Thank you. So this is all joint work with Sol Schleimer, who does not look like this, even though that looks like it's a photograph. So what is the 120 cell? It's a four-dimensional regular polytope. So this is sort of a four-dimensional platonic solid. Like the platonic solids, the faces of the platonic solids are polygons of sort of one dimension down. And so the same thing happens here. The 120 cell has 120 dodecahedral cells and a large number of pentagons, edges, and vertices. How do we draw this picture? So very briefly, this is radial projection. We radially project this four-dimensional object onto the unit sphere in four-dimensional space, and then we stereographically project that into three-dimensional space. This is a picture of the same process one dimension down, projecting from a sphere in three-dimensional space to this two-dimensional plane. How do we visualize this? What is going on here? So there's one dodecahedron right in the center of the whole picture. And then surrounding that dodecahedron, there are 12 dodecahedra at distance pi over 5. Y distance is measured in angles because we're on the surface of a sphere. It happens to be a sphere in four-dimensional space, but you can still measure angles distances using angles. Surrounding this, there are 20 dodecahedra a little bit further out, and then 12 dodecahedra, and then 30 dodecahedra. These are at distance pi over 2. This is the equatorial sphere halfway between the North Pole and the South Pole. And then these continue outwards. There's another 4 layers of dodecahedra moving further outwards. Here's another way to visualize this. So what you can do is you can make a ring. What do? You start in a dodecahedron, and you choose a pentagonal face to go through into the next dodecahedron, and then you carry on through the opposite face and go all the way around, and eventually you come back after visiting 10 dodecahedra. If you start in another dodecahedron sort of nearby and go kind of in the same direction, you get another ring of 10 dodecahedra. And this central gray ring of dodecahedra is actually surrounded by 5 other rings of 10 dodecahedra. And at this point, you have half of the 120 cell because you started with 10 dodecahedra per ring, and you've made 6 rings, which is 60 dodecahedra. Where are the other 60 dodecahedra? So there's another 6 rings that wrap around this one. Here's the 7th, 8th, 9th, 10th, and 11th rings of 10 dodecahedra each. Were actually inside of the 12th ring of 10 dodecahedra, so I can't show it to you. So we wanted to 3D print this because we like 3D printing things, of course. And there's a problem. So when you arrange objects in a printer that are supposed to be loose that you can put together, they can't be touching because they will come out of the printer fused together. And we could only actually fit 2 of these outer rings around this central gray dodecahedron. There wasn't a way to arrange them so they wouldn't touch otherwise. But we made this, and it works, and you can sort of break it apart and put it back together again. But we really wanted to do all 5 of these ones around this central gray this central gray ring. And so we're going to cheat. We're going to remove these 4 largest outer dodecahedra to make what we call a rib, because it's gently curved and made out of dodecahedra. And if you use 5 of these, then you can make the ring here. And of course, because they're not linked with this gray ring, you can print them separately without any problems of the printed objects getting stuck together. Let's remove that gray ring because we don't actually need it. We've got this beautiful object here, which is a puzzle because you print it separately and then you have to put it together. And so this is called the DC30 ring puzzle. If we could switch to the Elmo briefly. Elmo, please. So this is a large model of this. Here's a smaller one. This is our gift exchange this year. So you get these 5 pieces and you have to make them into this. It's very fiddly at this scale just to prove that this is really made out of these pieces. I can take it apart. Let's switch back to the slides, please. So what else can you do? So here's another decomposition. We start with this sort of straight rib piece, and then you can arrange 5 small ribs around there, and then another 5 around here. And this is a puzzle we call the DC45 meteor puzzle. These 11 pieces have to be combined together to form this object with dodecahedral symmetry. We settle on 6 different kinds of ribs. So there's this sort of straight one, and then there's varyingly curved pieces of varying lengths. And with these, you can make a sort of astonishing array of different puzzles. They're all held together just with the tension of the plastic. There's no magnets or anything like this. Here's a very brief puzzle for you now. 2 of these are photographs of the same object seen from different directions. Which ones? Any guesses?
That one and that one.
Yeah. I lied. In fact, there were two pairs. This is the same as this, and this is the same as this. The moral of the story is that these photographs don't do it justice. You should really come and have a look at them yourself with your stereo vision and try and put these puzzles together. I think I have enough time to just say a little couple of other variants on this. So if instead of the cell-centered projection, you use the vertex-centered projection, you get a different sort of arrangement of the dodecahedron three-dimensional space, which is entirely incompatible with all of the other ones, but it makes a different puzzle, which we call the DV30 asteroid puzzle, and these 6 pieces come together to form this object. And you can also do some things with the 600 cell, which is another of the 4-dimensional regular polytopes. This time the ribs have handedness. Previously they had mirror symmetry, but these 20 pieces come together to form this. And nothing else works. None of the other polytopes have enough cells to do anything interesting with. Nothing works. It seems that nothing works in Euclidean space and nothing works in hyperbolic space. So this is all you get. Thank you very much.